let us see an example of organic chemistry, of an organic chemistry question from a past exam paper, like this one, for example. In each section of this question, an organic compound is shown. For each compound, give its name and answer the questions about it. So here is the first one. We need to find the name of this compound. Okay, they give it to us in this form, but we can, I prefer if we redraw the compounds into the structural form, the displayed formula. So in this case, let's see how 1, 2, 3, connected to that, 4, 5, 6. We have 6 carbons, 1, 2, 3, 4, 5, 6. It's a chain of these 6 carbons. And the double bond is in the second carbon from 1 to, let's place a double bond there. Now let's add the hydrogens. That would be hydrogen here. There's another hydrogen there. Now this carbon here, 1, 2, 3, 1, 2, 3. Yeah, it's connected, as we can see, as a methyl constituent there. 1, 2, 3. There's another hydrogen. This has 2 hydrogens, and this has another 3. Okay, so this is actually the displayed formula of this compound that they give us, and perhaps it does help to name the compounds and see exactly what is connected to what. It's a more clear picture, I believe. Anyway, so now let us see where we have a chain of 6 carbons. Let's see how do we start numbering the carbons, from the left or from the right. Well, the double bond here, it's stronger than the methyl constituent. So we'll start from the side which is nearest to the double bond. So this would be carbon 1, 2, 3, 4, 5, 6. So we see that already we see that there are 6 carbons here. It's an hexene because there's a double bond. Now let's name it properly though. So, okay, we start with, okay, this methyl, this alkyl group is connected to carbon number 4, and it's one of it. So we start from with the name of the alkyl group first. So it's 4 methyl. So there's the methyl. Okay, now this is, we have 6 carbons, so it's an hexene. Methyl hex, let's, but now the double bond is at the carbon number 2. So we have to place here a 2 and the ending of in. Corresponding to the double bond. So this, the name of this hydrocarbon is 4-methyl-X2-ene. All right. Okay. Now this compound shows stereoisomerism. Okay. Understandable, it's such a long chain. We have a methyl group there, and we have a double bond. Okay, so this compound define stereoisomerism. Okay, whenever we have, there's always some question of the sort, like to define something. Okay, what can we say here? The molecules with the same molecular formula and structural formula. Okay, let's start writing. What is stereoisomerism? These are molecules with same molecular and structural formula, of course. Molecular, this is obviously, this is implied in any case, and structural formula, structural formula, with different arrangement, with different arrangement of atoms or groups. Here, or groups. Well, here we have a methyl constituent groups. So we see that first of all, this group here, this methyl, this alkyl that is connected to carbon number 4 could be at a different location. It could be to some other, perhaps carbon 5, or it could be on the other side as well. That could be here, for example. So it could be on either end of the double bond. So already we can have 2 of these. Also, take a look at this carbon here. This is a chiral carbon. Chiral. Chiral means that a chiral molecule actually is one that has a chiral carbon. And what is a chiral carbon? Is one that is connected, the 4 bonds that it makes with different items. They're not like one type of alkyl here and another one over there, and perhaps a hydrogen and some other alkyl over here. Now this carbon here, it is chiral because to the left is connected to this methyl group. To the right, it's connected to another group that has a double bond. It's an alkene of some sort. And it's connected also to this methyl here, and on the other side it's connected to a hydrogen. So every single bond, in other words, of this carbon is connected to something different. So this is called the chiral carbon, and this molecule is called the chiral molecule. So altogether here, we can say that it has like 4. State and explain how many stereoisomers. It can have like 4 isomers, stereoisomers. Okay. So 1 chiral center, 2 with different groups on either side of the double bond, and also the double bond alkene. All right. Now let's go to the next compound. Now this time, again, we are asked to find the name of this thing. We see again a double bond there. How else could we write it? It's displayed formula. Let's place the double bond, the carbons bit of the double bond in the middle. It's symmetric. This molecule is symmetric. And here we have the carbon connected to 2 methyls and the other carbon as well. So we can show it in this configuration. Okay. The name of this compound. It's also another hydrocarbon. Okay, let's take the longest chain. It's could be 1, 2, 3, 4. Could be this one, or could be that one, or this one. It doesn't matter as long as we have. It's the same as long as we have the double bond included in the chain and the biggest number of carbons in the chain. So the biggest number of carbons is 4, really, no matter how we go this way. Okay, let's make a different color to show the chain we're going to choose. Let's make it yellow. So we can take this to be our chain, okay? All right. So let's say 1, 2, 3, 4. Name the carbons. And now if we take this chain, we see that there are 2 groups here connected to the carbons of the double bond, 2 methyl groups. So where are they? 2 at the carbon number 2 and carbon number 3. So the name here would be 2, 3. We have 2 methyls, so dimethyl. We must not forget the dimethyl, because we have 2 methyls, one here, one there, dimethyl. And because we have 4 carbons in our long chain, it's a of the type of butane, butene actually, because we have a double bond. So two in. Okay. So actually, it doesn't matter if we were to start from here, counting carbons 1, 2, 3, 4, because it is symmetric. Okay. So anyway, so 2 there because the double bond is at carbon number 2 here. 1, 2. All right. So this is the name 2,3 dimethyl butene. All right. Draw the skeletal formula of the organic product of the reaction of this compound with cold dilute acidified manganate 7 ions. When they say manganate here, they mean actually this type of ions, manganate. Like, for example, it could be part of potassium manganate. They call it manganate, but others would call it potassium permanganate, not manganate. Anyway, so they call it manganate, and in your book they also call it manganate, and it's better to know it in this name. This is an M, manganate. This is an example of where this manganate can come from. Not negative there. It could be part of potassium manganate, for example, these manganate ions that they are talking about. Usually this is what it's used. And what does it say now? With cold dilute acidified manganate. That's important, cold and dilute, because if it was hot and concentrated, the products would be different. And in fact, this problem is actually part of the oxidation of the alkenes, the reaction of the oxidation of the alkenes, which is on page 210 in your textbook. And here it's exactly that. It's just the example of the alkene involved in this question is a bit different. It's bigger than the alkene, that the example of alkene that they have in the book. So we need to bear this in mind. Now, what does the question say here? Draw the skeletal formula. Now, the skeletal formula is the one that is given with a zigzag configuration where we don't show the carbons. Now, with cold, now let us see first of all, before we write the formula, if this compound, this hydrocarbon, kind of undergoes an oxidation reaction in dilute and cold ions of manganate ions, what would be the reaction when it's obviously this would not obviously, well, we need to know, because it's dilute, etc. It will react with a solution, actually with the water, and what are we going to have there? It's like it's the reaction between an alkene and water. So let us write here the alkene with a double bond. This would be the 2 methyl groups on each side. Okay, and this now react with water. Let us write it in. We can write it in this configuration, I think. All right, and remember, this is going to be now an oxidation. Let's remind ourselves that this is an oxidation, includes some. Okay, how do we represent oxidation in organic chemistry with this oxygen in the brackets? And this now, what will result? The double bond will break, and the double bond will break, and each of these carbons, there will be the formation of a diol, which means two hydroxy groups are going to join to this alkene, and the double bond will disappear. So what will be the product of that now? So let me yeah. Okay, let us, all right. So that, how many? 1, 2, 3, 4. 1, 2, 3, 4. In the middle carbons, we'll have the carbons that were involved in the double bond, that is. We have 2 hydroxy groups, and the remaining is what was there. Okay, so this will be hydrogens, and this will be hydrogens. Let's show it. Maybe I should, sorry, let me represent them as like that to remind of this initial configuration of our molecule. And here, this one, let's also show clearly the methyl. Okay. So you see the 2 methyls are still there on both carbons, but in addition, the double bond here broke, and we have the 2 hydroxy groups now attached to it, and there are no more double bonds. So we see that is why this is an alcohol. It's actually a diol. It's a characteristic product when an alkene kind of reacts with cold and dilute acidified manganate. The product is this diol. It's a type of diol. In other words, di, because we have it's double the alcohol somehow. It's a diol. All right. And now, what does it say now? Draw the skeletal formula. The skeletal formula of this, this is the product. Let us draw the skeletal formula. Where can I draw it? I can draw it down here. Well, we have 1, 2, 3, 4, we can say. And we have a hydroxy here and a methyl. And on the next carbon, again, the same thing, again, the hydroxy. We can tweak up there to look symmetric. So this could be the skeletal formula. I must tell you that in the memo, they show this formula as a straight line rather than a zigzag. I don't know which one do you prefer, but usually, anyway, let me show you how it shows in the memo. It shows like that. So they don't show it as a zigzag, but it's the same thing, okay. And of course, the hydroxy doesn't matter if it's down or up, because it's the same. You know, when we have a compound with single bonds, we need to remember that these compounds are not like rigid, they can rotate. So, for example, this hydroxy can rotate and go up there, and this bond comes down. So but it's the same thing. It's not a different kind of, like an isomer or something. So either way, I suppose it is correct. Now remember, now this is the skeletal formula of this product from this equation, all right? From this equation, from the reaction of our alkene with dilute and cold acidified manganate. The product is always a diol, okay, which we got it there, and it comes from the reaction with the addition of this water, the hydroxide is from the water, and the double bond breaks. Now, it's the next question says, name the organic product of the reaction of this compound with hot concentrated acidified manganate ions. So you see now, here we had cold and dilute manganate ions. Now they say hot and concentrated. Now this results in a different product, not a diol anymore. And it's again, but so with hot and concentrated acidified manganate ions. Now, maybe we should find some more space here, maybe to discuss what the products might be of an alkene reacting with in these conditions with hot and concentrated acidified manganate. Now, let's see. So, find some empty space. You see, again, it's on page 210 in your book, fortunately. Everything is here, the information that we need to answer this question, but be careful because the example that they use in the book is a more simple alkene. It's not. Now, what happens here? So we have now the case where's the pen, all right, where we have our alkene. In our case, this is our alkene. Let's write it again. It has this kind of form, yeah. So we have this alkene which will react under conditions of hot and concentrated manganate ions in a solution of manganate ions in a solution of this type that contains this type of ions now, which these are now harsher conditions. Now, again, the double bond will break, but let us look first of all at, in a case where we have, it depends on what the products can vary, and it could be a ketone or an aldehyde or carboxylic acid or carbon dioxide, depending on what is connected with a carbon, this carbon, one of the carbons of a double bond. So in the case, for example, where we have just, instead of these methyl groups here, if we have just hydrogens, simple hydrogens in the double bond and the other carbon with something else, it doesn't matter, then the product of this type of hydrocarbon will be carbon dioxide. Why does it write like that? Carbon dioxide and something else. So it's just carbon dioxide and something else, depending on whatever is there. But now, if one of these is not a hydrogen, but something else, some alkyl group, if one of the hydrogens, like this one, say some alkyl group of some sort, and this is another, the remaining is the same, then the product will be actually an aldehyde. So after oxidation, this is oxidizes, and the product will be an aldehyde, which means that will be of the form, this one will look the same, but here we'll have the functional group of an aldehyde, whatever else. So you see this, here we got carbon dioxide, but here we got an aldehyde, because this is the group, this part here is the functional group that represents aldehydes, isn't it? This part here. Now this aldehyde could be oxidized even further, and the product of this further oxidation will be a carboxylic acid. So how can we end up with different products, like what would be the carboxylic acid. Then this would be carbon with the oxygen, and this constituent will stay there. And now we have this part, which is the characteristic of the carboxylic acid, the functional group of carboxylic acid. So this was here an aldehyde. Let's write aldehyde, and this is a carboxylic acid. Carboxylic acid. Okay. And finally, if both of these constituents are not hydrogen but something else, finally, the last case would be when these are both different alkyls, like alkyl 1 and alkyl 2. There's no need to be the same, isn't it? And what happens in this case now, after oxidation, then the product will be, okay, this will stay again the same as in the previous case. That will be the R1, that will be the R2, but here, with the addition of, we'll have the oxygen, and this is of course now a ketone, because this part, this carbonyl in the attached to the carbon, which is not a primary carbon, this is a characteristic, the functional group of a ketone, where the carbonyl group is somewhere in the middle, not at the end, in other words, of the carbon chain. All right. So these are the three possibilities. Now, in our case, in the exam paper, we have this particular compound. Okay, in which category does it belong? Look at that is the reason why we drew it this way, to remind us of this type of configurations of the molecules. We see that that these two items which are attached to this carbon, these are not hydrogens. So it's not this case, and it's not this case. So obviously it's this case at the bottom. So the product of this alkene that we have at hand in our exam will be a ketone. I mean, when it reacts with hot and concentrated manganate ions, isn't it? So now that we know that we are going to get a ketone in our case, and frankly, what will be this R1 and R2 of the ketone? It will be these methyl groups. So let us go back to our exam now, if we find it. I think it's here. Okay. So it says, draw the structure of the part of a molecule. Where are we now? No, here we are in this question number 3. Name the organic product of the reaction of this compound with hot concentrated acidified manganese. Obviously, it will be a ketone, isn't it? A ketone, and which ketone is this going to be? Because we had, remember, we have this product, and these two are two methyl groups. This will go away, and we'll have here the oxygen instead of these other two methyls. So our compound is actually this type, and this will be the oxygen. You see the ketone here is the carbonyl group. And how do we call this? What was I saying now? What is the name of this ketone here? It's 1, 2, 3 carbons. It's a propanone, obviously. Propanone. All right. Oh, yeah, 12 o'clock. All right. Draw the structure of a part of a molecule. Anyway, I think we must stop here, and we'll continue with this problem next week. I will try to do it properly. Okay. So thank you, guys, and.